Matthias, the CEO Trusted Advisor. Today is all about Fabric IQ. Pretty new feature just from the presses from Ignite in San Francisco in November. We will have a technical overview like architecture and come and ask questions, and after that we will have a demonstration. So let's start. As always, we will start off with the Fabric periodic table. Fabric IQ is already integrated. You see that's a pretty new feature. We have already naming proposals included, the key features listed, the documentation, and Fabric CLI is not yet available. This is the logo that was shown at Ignite, Fabric IQ. So let's go a little bit into what's the idea, what is all about. So when we start off, we start as always with our OneLake foundation. So let's draw OneLake foundation, let's say here. So this is OneLake. It's our foundation. And in OneLake, you have some sources that can serve as an input for Fabric IQ. The first one is Lakehouse. The second one is Eventhouse. And the third one is a semantic model. All these can act as an input, but there are differences in that input in the way they can deliver some input. The point is that once we move up into Fabric IQ, so let's take this one as Fabric IQ here. This is Fabric IQ. Fabric IQ is all about ontology. Ontology is like a semantic model, so it defines like tables, but the tables in this case are entities, and you define relationships, but the relationships in this case are verbs. What's the difference? Difference is that in an ontology you can model your different business objects, like, I don't know, cars or products or customers or something like that, and then you can bind metadata from different sources to these entities and define relationships from one entity to a different entity, but not only the cardinality, but also like a verb, so uses or has or books or something like that. So it's much more general, and the idea is that you model a part or the whole business in that and not just a data source. So, it's all about ontology, and you define like your enterprise vocabulary. Enterprise vocabulary. I like that because it's more or less native, right? So when you want to define your ontology, you have different data sources. The first one, like Lakehouse and Eventhouse, they are used for bind your data, which means that you need to define the ontology in the Fabric IQ layer, but you can bind the metadata to the ontology out of Lakehouses or Eventhouses. When you have a semantic model, you can simply inherit this semantic model schema. Because you have already defined a schema and you can build on top of that. Once you have defined your ontology, you can start using that ontology. And there are different ways how you can use your ontology. The first one is you can visualize your data. So visualize. Visualize your data. This is done through the meaning of a graph, because in the end it's like graph data that you define, right? And you can display that, for example, in Power BI reports or in notebooks. The second way that you can consume the data is like that you can query the data, or that query. And the way how you would query the data is through a data agent. This is kind of interesting because in that way you will give the data agent much more context about your enterprise than in simply throwing in some data. It's much more descriptive. You have all the relationships, all the cardinalities. So you could expect more and detailed answers once everything is correct. So then the querying is through, let's say, Copilot or natural language. And there's a third way, and this third way is kind of new. So I can draw it in red. It's called the operations agent. The purpose of, or the idea of this operation agent is to create alerts, which means it sits on operational data and creates alerts, all of that. Then currently it's consumable through the REST API. But I think you can imagine, it's not too hard to imagine, a variety of ways how you could consume alerts out of an operational agent in general. So how does this kind of ontology now really work? How do you do that? You start off with entity types. So define an entity types. Entity types like that. That's not beautiful. Let's make it beautiful. And there we go. Entity types. Entity types, you can also refer to them as blueprint for your enterprise. So what could be possible entity types? Just take an example. So for example, you can start off with something like, let's say, a customer. And the second one could be like an order, and the third one could be a product. Let's take it simple. So you have order and you have product. For each of these entities, you would define a different metadata, like the customer ID and the customer name, and let's say the customer email, and let's say some lifetime value about that record. Regarding the order, you will for sure have some kind of order ID, an order date, and an amount, and a status. And regarding the product, of course, you will have a product ID. You will most likely have a product name, a category, and a price. So now the interesting part begins, because you define relationships. So a customer places an order, and an order contains products. So these are the relationships, and the interesting part is you don't not just only define the relationship and the cardinality, but you also define, like a verb, how this works together. And just think about how this helps a large language model to understand what's really going on. You have also kind of static data or properties that you can define. So for example, you could define a time series property. The time series means that it varies over time. So it's like a slowly changing dimension with expected change, right? So all values are attached to date time. So let's say you have, I don't know, a temperature. In addition with the location. And the source could be an event house. It's not beautiful. Event house stream. Then you would also attach this data to the appropriate entity. So for example, let's say a customer doesn't have a temperature, obviously, but let's say an order, if they needed some fridge, right? It has a temperature attached to a time. Right, so things must be kept cool. That means that you assign a temperature that should not exceed a value, and there you think, of course, about the just defined data operator agent. So this is the way how it works. So you have like the entity types, right? Yeah. You have the relationships, and you have like static metadata, for example, the time series in this case. So let's take that a little bit from the different point of view. Let's start with our ontology. So we are defining our business model. We are defining our business objects and how they interact with each other. So let's take, of course, it's very simple. It's just a sample, right? So let's say we have an entity type, which is a store where you can buy stuff. You have a store ID, you have a store name, and you have a city where the store is located. Next, you have this streaming data, which is the property temperature value. Yeah, property temperature. Type is float. Time series is true. And unit is Celsius. Let's say that. And next, you define the relationship between these both. Relationship located at the source. The source, let's say, is our freezer. And the target, in this case, is the store where the freezer is. The cardinality is n/1. We can have more than one freezer at one store, but obviously not the same freezer in different stores. So how does this like propagate back to our lakehouse and to our data binding process? So when we go back to our lakehouse, let's say we have a lakehouse with a table, and the lakehouse table is dim store. And there we have the store ID, the store name, and the city. Everything defined just like a traditional table. And then we have an event house stream that continuously gives us the telemetry, the freezer telemetry data, which is the freezer ID, the timestamp, and the temperature. So now let's connect that stuff. So let's bind our event stream and our lakehouse table to our business data model. So first, we bind our Lakehouse table to the entity type store. This is a binding process, which is basically a column mapping. So we map our store ID to our store ID. We map our name to the store name. And we map the city to city. This is a simple mapping, data binding process. Next, we map our our stream. The stream will end up in our property with the temperature value. So we will bind here the primary key store ID to the foreign key freezer ID, and thus create our temperature together with our location data. So this defines like both. And from there, because we have streaming data, we of course need some data quality check to ensure that the data is fine. This mostly accepts the streaming data because temperature data could be wrong at one point or something like that. So before we give this data to, I don't know, visualizations or something like that, we need to attach some kind of data quality checks here. So this is basically how all that modeling stuff works. This is basically the idea. So you might ask, okay, that's cool. Thanks, Matthias, for pointing that out. But I have already a lot of semantic models. So when should I go with a semantic model and when should I go with this new ontology stuff? So I thought a little bit about that, and here's my decision tree. So the first decision that you have to make is, do you need cross-domain consistency? Cross-domain consistency. Cross-domain means data domain. So you have different data domains. These different data domains define the semantic models. Do you really need cross-domain consistency? When you need cross-domain consistency, you will not achieve that without a bunch of stacked semantic models that are quite complicated. So let's assume you say, yes, I need cross-domain consistency. Then the next question would be, do you have complex relationships? So when you say, okay, yes, we have complex relationships, then you should go not only with ontology, but also with graph to bind this complex data together. Use cases could be supply chain, IoT, relationship traversal, things like that. When you say, okay, no, we don't have complex data, then you might be fine with just ontology to define the unified vocabulary. Just remember this enterprise vocabulary idea. I like that a lot because it describes the need for an ontology. When you say, no, we don't need cross-domain consistency, then the next question is, do you need real-time data? When you need real-time data, you need to bind basically Eventhouse and Lakehouse data together. Then you need to use the ontology again. For real-time monitoring, for time series binding, and so on. When you say no, then you are really fine with semantic models. with the traditional style schema, all the stuff you like. So, well, let's go a little bit through it. So examples could be like, this is, for example, complex IoT stuff. This could be an example for questions about how are things related to each other. So let's just say a 360-degree view of the customer. The real-time data could be IoT with real-time data, real-time alerts, something like that. And the semantic models are just like semantic models, for example, sales data and all the good stuff that you already know. So this is basically the idea when you need ontology and when you need semantic models. But as you remember, you could derive an ontology from a semantic model. We have seen that here. So the truth is that you typically stack that things. Means for each data domain, you define your semantic model, semantic model, semantic model, semantic model. You might even stack these semantic models for different reasons. So this is like the data domain view. Let's write it here. And next layer is that you define an ontology on top. And combine all these semantic models and maybe even event houses and whatever. So this is like the best of both worlds. You still have your semantic models, and the ontology view gives you the next step that is possible on top of that. So let's have an end-to-end workflow. Let's see how that looks. So phase one is design. Very important. When you play around with the interface, you will see that it's kind of a little bit hard to use. So you need to know where to enter what. That's really important. So the phase one design means you define your ontology. Not directly in Fabric, but maybe in the flowchart, on the paper, I don't know, somewhere. You define your properties. You define your model relationships. And you set your constraints. So all that stuff you define in the phase design. Phase two means bind. Bind means combine your data with your ontology model. First, you bind your static data. Bind your static data like Lakehouse tables, like column mapping, and like key selection, foreign and primary keys. Next thing is bind time series. Bind time series means that you bind your time series data like Eventhouse streams, like timestamp columns, and like value columns. And the third step in phase two bind is bind relationships. Relationships means foreign keys, like cardinality. Everything of that is bind relationships. So this is phase two, bind. Phase three is generate. Now you create your graph. Generate. generate your graph, process your bindings, create your nodes, create your edges, attach metadata, all that stuff. And once you have created your graph, you need to validate that. Validate means entity count, relationship count, data quality in general. Why? Because you combine data in a new way, and that's always a bit tricky. That could go wrong. You know that from join stuff, you would always check join stuff, same as here. Phase 4 then is query. Query your data. For example, with GQL queries, for example, with KQL queries, for example, with natural language queries, data agent. Query your data, try your data, test your data, find patterns, ask for paths when you query the graph data, go with conversational UI, with natural language, and phase 5 then is integrate. Integrate your data now in Power BI, reports, in notebooks, or in natural language, so it means data agent, or in external apps. So this is basically the way how you should proceed. This ensures that you have a proper design, a proper binding, a proper querying, until you went with the data to some places where they're much harder to validate. So this is like the architecture overview. There are questions in the community, and there's some important informations. So first, Fabric IQ, the ontology, is in preview, which means it can change. Support is, of course, very limited. You are like an early adopter, which is great, but be aware of that. We have community discussions already. So first one is, when should I go with ontology and when should I go with a semantic model? This is quite hot. Question is, I already have Power BI semantic models. Why do I need an ontology? So answer is, ontology is not meant as a replacement for semantic models. It's a layer above the semantic models. Use an ontology when you need cross-domain consistency, when you need to combine real-time data and historical data, integration Eventhouse and Lakehouse, when you need AI agent grounding with very, very solid data, when you need graph algorithms like relationship, like path finding, and when you need complex relationships like supply chain, IoT, and multi-hop reasoning. Semantic models are the right choice for traditional BI, DAX measure, star schema, and so on. You can and you should use both together. Next question is, hey, there's a blocker called direct lake. Question is, I tried to generate an ontology from my semantic model, but it only creates definitions, no data bindings. Why? The answer is, only direct lake supports full data binding and querying. Import mode and direct query mode will only generate entity type definitions, which is called a schema, without bindings to actual data. We should migrate to direct lake first. So direct lake is a requirement. Next question. Time series bindings are not auto-generated. I generated an ontology from my semantic model, but my Eventhouse streaming data, in this case the freezer telemetry, is not included. I have to bind it manually. Why isn't that automatic? Answer is, time series bindings are not auto-generated because they require additional configuration, like which property should be the time series, which column is the timestamp, which column is the value, which entity type does this belong to. Fabric can't infer this automatically. You need to configure this manually. Next thing, hey, there's no versioning. I'm designing an ontology for my whole enterprise, but there's no versioning in preview. How to handle schema evolution? What if I break something? Answer is yes, there is no versioning at the moment. You can export the ontology to JSON and then do the versioning on your own. You could use naming conventions in defining the ontology version 1 and version 2 and so on. But these are at the moment workarounds. Next question. Natural language is like a hit or miss. I'm building an ontology data agent. I ask more complex questions that doesn't work. Answer is yes, it can have a variety of reasons. There can be double namings like store entity with store verb. There could be missing relationship context. There could be very complex temperature logic, like when temperature exceeded. The question is, what does exceeded exactly mean? And it could simply be that you need some kind of prompt engineering because your prompt is not perfect. Then there are some general questions like, is Fabric only for big enterprises, Fabric IQ? No, Fabric IQ can be perfect for small and medium business sizes. Depends on what your business is and whether the idea of ontology really helps you, but it is not a question of the size of the business. Next question is, can I use Fabric IQ without Power BI? Yes, of course you can, no problem. So this is like from the architectural side. Let's jump over to our labs. Let's go to the practice part. We are in our beloved Fabric. We click new item, and first, as always, we need some data, which means let's create a lakehouse. This is the ontology lakehouse. At this moment, public schema should not be enabled. And next, what I do is I load data in. I have shortened this part a little bit because first I upload the data, and then you will know that I need to create a table out of each and every single file. So we can well, you go over that. You see it works like that, and load two tables and then new table. And then we simply hit load because the data is well prepared. So I have done that. Next thing that we need to create is an event house because we will put in some event data. This is, of course, sourced from a file, so no real event data, but real data from an event house. Let's create that. And next, what I will do is I will load a file into the event house. After all this greetings and welcome dialogues, you see we have the query set and the table. There is no table at the moment. So we can simply hit new data, and just in the middle, the big green button, this one. And then we can say local file, select our file, and then we can, out of that local file, create a new table and name that new table properly. This is a freezer telemetry data. We can browse for files or do a drag and drop. I did a drag and drop with a freezer telemetry, CSV. All these data sets have very little data, which is helpful because I already pointed that out in the architecture part. All the data quality is a big issue here because you create new relationships, and given the fact that we have small tables, makes it simpler. You see data activity trackers here, or our data is in here. So everything is in place. We have the ingestion mappings and the timestamp and so on. All that what we need is available. So then we can simply move on after we have checked our data quality, which is not a big issue in this case, obviously. And the next thing that we want to do is finally to clean up and to create our ontology view. See, it's enabled. You need to enable this preview, and let's give it a proper name. Our ontology, this is a retail sales ontology. Let's create that. It's not built on top of semantic models, but directly on OneLake. I pointed out that you have both options depending on your business needs, what you want to do or what you not want to do. Then now it's creating the ontology preview, which takes a second. And after this happened, we can start defining our ontology. When you remember, it's like first we plan, so we define our entities, and next thing is that we attach the metadata to this existing ontology. So here we go, and we can add an entity type. Type this, name this entity type. It's like store, and now we can add that. And add properties or add bindings. These are our two options. So in this case, we will go to add bindings, and then there we go, and add the data to the entity type. Now we see all the lakehouses that we have. Our one that you want to go is with the ontology lakehouse, and now we can select the table source or the source table, which in this case is dim store. We get all the columns, the source, and the property names because everything is properly named. There is a high level of auto matching. So we can simply save that. Everything looks really great. You see, even the longitude is matched. So we have defined our first entity, and in that way, we will now define our remaining entities. For every entity, we need to set an entity key, which is usually the ID, but we can also define composite keys when this is really needed. So let's add the next entity type, which in this case is product. And you guess it, we go to bindings, and then we select the ontology lakehouse and select the product table, then product. And we have again all the columns loaded, so we can save that and move on with the defining the key. I show this because I think it's helpful for the interface. I hope you find it too. So next one is calendar date, which is a time series. And we again add bindings here from our ontology lakehouse, and see it's dim date. This is the date table. We create that, and I have also to define a key, which is date in this case. Now we add, see that the sales event entity. In this case, we don't add bindings, but first we create the properties. Look at the properties, and then we create the bindings. You can do both basically, and we will do that later on. So you can first add the properties and then map the bindings, or you can do quite like both in one step, but the result is the same. You need to define the key, which in this case is the store ID, combined with the sales ID, with the product ID and the date. So this is a composite key that we need. And next one is that we cross-check everything in place, and then we will add our last entity type, and we need to define the relationships. So the relationship, as I pointed out, are verbs. The first one is has, so store has a sale event, so this now is defined. We need to select the workspace, the lakehouse, and all that stuff to nail that. I had the issue that at one point, that's Fabric IQ, excuse me. There it is, go a little bit up. My fault. I had it at one point that the relationship was not properly stored, so I needed to go back and redefine it. So be aware of that. It's a pretty new product, and things cannot be very could be not very polished. So we refer to the fact sales table. Next, we define the store entity type, which is the store ID, and the target entity type, which is the sales event. And now we need to map the store ID, the product ID, and the date. And you see what we need to map is always the key that we have defined, the primary key. And so then we can create that thing, and the relationship, the has relationship, so a store has a sales event is now created. Next one is sold in, and you can imagine it's about the product and the sales event. So product is sold in a sales event. Again, we need to define the properties, and next one is occurs on. This is a relationship from sale event to the date, to the calendar date that we need to define. Last but not least, it's updating our ontology, which is really good. And last but not least, we then have to add our last missing entity, which is the freezer stuff. So let's check whether we have all the definitions in place that we really need. And the next step then is to define our entity once everything is in place. You see the interface is a little bit rough, so we could imagine more stuff here. And now we are at the freezer. So the entity type freezer. You see I have a typo here. The typo in general is not relevant, but when you think about data agents and large language models, those typos can become very relevant. And in this case, we first define our properties. We don't make it directly a binding. So the freezer ID model, it means safe temperature, and the store ID where the freezer is located. We need to check the data types, and now we can then add a binding and combine the predefined properties with our bindings data. Of course, as always, we need to define our primary key, which in this case is the freezer ID. So this looks good in general. Let's jump over to the bindings and add our binding from the ontology Lakehouse. There's a freezer table in. So let's pick that and add it. Yeah, you see it's now loading the source columns, and we have the predefined properties now. There's a simple match because they match by name, which is always very, very helpful. And thankfully to sample data, this is often the case, but let's cross-check. And after everything is fine, we can simply hit save. And this stuff is stored now. So this looks really, really good. So let's go the next step. Let's check. Yeah, bindings are in place. That's really, really great. You can edit that and or delete it later. That's also, I think, nice to know. And now we can add the entity type here, add data to the entity type. And now we remember we have the freezer telemetry. So we combine, in this case, two data sources, Lakehouse data and the Eventhouse data. We select the timestamp column. We have our properties like store ID and freezer ID. So let's add the static property here. You can do that with add static property, or you can add all source columns as properties. And in this case, we will select our freezer ID and map it to the freezer ID. We do that because you see the freezer ID needs to be in capitals. It's sensitive here. Then we check the timestamp, temperature, humidity, percent, and so on. This looks good, so we can save that data. So now everything is in place. We have 5 columns defined. We have defined the mashup between the Lakehouse and the warehouse. What's missing now is the relationship. So operates store, source data, freezer. So the store operates the freezer. You see there's still a typo in there, which could be an issue later on in the large language model. It will not for the query that we do, but you need to take care of these kind of typos, which weren't so important before. It was like not looking good, but not an issue in data retrieval. And with large language models, this is now So this is defining the relationship with source and target column. And let's create that. So this is fine. This looks good. This works. So now we can cross-check our data, and we have this entity type overview, which is quite nice. There we see the graph rendered. So you see calendar date, sales event occurs on calendar date. Store has sales event, and product is also related to that store. When we go to different entities, we can also see graphics in there. So this is helpful to give an idea whether the data makes sense or not, was properly defined. So now we can go again to our entity overview of the sales event. This is the sales event. And we can hit expand, and we will get new controls, which is a little bit tricky to know. But once you've got it, it's okay. You see screen space is nice, but case is a little bit limited. So let's add the freezer here, and let's add the operation. So the freezer is the store operates the freezer. And now what's really nice is, so this is like the data model. Now we can start playing around with that data. So what's possible now is we can add filters. So this is like the where clause in SQL Server. So we can say we filter for specific store ID, and when we then run the query, we need to claim a little bit space. See that here? And once we fiddled around with the interface, you see that that's the preview part. We get the result of the store ID in Paris. Then we can reset the filters, clean everything. I needed to clean the stuff multiple times so that it really worked. And then we load the data and clean again. That might be not more relevant when you play around with that. So let's create another query with the sales event and the store. And so then we need also to define the edge, the relationship. So then we can say, okay, the sales event has a US dollar revenue of greater than 150, apply. And once we run that query, we will see the result of that query. So this is true for Amsterdam and Paris. I think it's a really nice way to query and to see the results of that query. So this is like the querying interface. Last but not least, let's jump over to our data agents, and let's have a look how these data agents behave. So for doing that, we need to create a new data agent. I did that already. I pointed it to the ontology. So now we can ask a question, show me all times since where freezer operated by the temperature higher than minus 80 degrees of Celsius, and the total unit sold of that day. And we will get the result. It's analyzing. We will see the query language in a minute. It's the same like for to SQL or to KQL. So we see the ontology query here. It's still running and gathering the data. And in a minute, we will get a result. The result is limited. So basically it says I could retrieve some data, but not all, because the question was not absolutely clear. So what's aiming to find. So this is basically our demonstration. Much for being with me today. I hope you enjoyed the introduction Fabric IQ. I'm pretty sure there is more to come, and we will talk several times about Fabric IQ. Enjoy.